Okay, so we're here for Khaled's PhD defense. Khaled came to us from Diagenesis University in Libya via way of Colorado State, where he decided he wanted to come here instead. And he's been working on the Miocene in Benghazi, in Libya. And so he's going to present the results. If everybody remembers the format, we'll have the presentation, we'll have questions from the general audience, and then we'll have a closed session with the committee. Okay? So, Khaled.
Yes. My work is about the sedimentology, sequence stratigraphy, and chemostratigraphy and diagenesis of the Cyreniacan Miocene. There is Jebel Akbar, uplift, and Suluk Trough, northeast Libya. These are the conferences and population researches. We have 2013 APG in abstract in Pittsburgh, and 2013 at Houston Student Expo, and in 2014 we had just one with the APG, but in 2015 I was very lucky, I had 6. Three of them are extended abstracts. The first part is the sedimentology and sequence stratigraphy. And this, in here, the first thing we're to introduce is the study area. This is the map of Libya. This is the Mediterranean Sea. And this, the green part, is the study area. And here they enlarge it. Satellite image. The 2 red lines here are escarpment. The first one we call it lower escarpment, and the second one is the upper escarpment. And we got most of our described sections in the field along these escarpments. The objectives for the sedimentology and sequence stratigraphy part, to have detailed documentation of our of the Cyreniacan Miocene sedimentology and sequence stratigraphy. And we did that through 29 measured sections, field measured sections, besides gamma ray profiles measured in the field using handheld scintillometers. And the spacing was 0.5 meters in between the intervals. And we used the carbon stable isotope Curtis to have better age control. This is the geological setting of the Cyrenaica. Cyrenaica basically is made up of, is a stable platform in the central Mediterranean. And it has 2 tectonic provinces, Al-Jabal Akbar north and Cyrenaica platform south. And it has 2 troughs, the Marmarica trough in the east and Suluga trough in the west. And the other good thing about the Cyrenaica, it's preserved structurally and sedimentologically because it's escaped like severe tectonics. Here, the previous studies in the Cyrenaica, they started like very early in the beginning of the 90s with the Italians, but the documented ones started like the mapping program started in Libya, started in the 1970s. So they started here in the Jebel Akbar in 1974, and the Miocene, they call it Rajma formation, but there's another people, they work in Suluga Trough, which is in the south, and they call it Rajma group, and they find out there are like 3 formations in this group. Benghazi formation, Shledima formation, and Musus formation. But here they call it just members, Benghazi member and Wadi Qatar member. 2 different groups mapped 2 areas. And then later the Jebel Akhdar Rajma formation raised up to Rajma group, and they expand the age from just middle Miocene to middle and late Miocene, and they call it Rajma group, and Benghazi became a formation, and Wadi Qatar became a formation in the north side of the Jebel Akhdar. So we have Rajma group in the north and Rajma group in the south. And this study, when we use the stable isotopes, the range of the Miocene outcrops is wider than what they were thinking here. It becomes like including early Miocene, middle Miocene, late Miocene. With the other thing, we find out these formations are not synchronous. Their boundaries are not synchronous, but they're dichronous. The methods here in the stratigraphy, sequence stratigraphy and sedimentology, as I said before, we use it in this outcrops. It's around 130 kilometers or more. We use it we measured 29 sections in the field. We use it 14. We measured 14 gamma ray, spectral gamma ray profiles, and intervals between the measured points in each section was 0.5 meter. And the other thing, we had panoramic photographs or photomosaics to annotate facies in the field. The second part was the lab part. We did the thin sections. We made thin sections to study the Petrography and Diagenesis for 503 samples, and again the interval is 0.5 meters between each two samples. And we used the same samples to do the stable isotope oxygen and carbon. And the thin sections, we used them to identify the components of our lithologies, cements, diagenesis. Also, later we added the trace and common elements using the XRF machines here in the department, in Texas A&M department. And the first thing we come up with, the sedimentology. Here we find out this Miocene outcrop Rajma group has 11 facies. 9 of them carbonates and 2 of them siliciclastics. And we group these 11 facies into 3 facies groups. We call them peritidal facies, includes evaporite, basically gypsum, microbialites. We have stromatolites, thrombolites, and laminites, with cryptal laminites. Palaetal backstone, waxstone, porites, bioplastic backstones. Very fine porous sandstones and green shale. And the second group of facies is the ramp crest facies, which is basically just oolitic grainstones. And the subtidal facies is bioplastic carbonates, reworked bioplastic carbonates, red algal reefs, and reworked red algae. Here's our depositional model. We split them through time: early Miocene, middle Miocene, late Miocene. And on the sides here, this is the southern part and the northern part, where we add the parasequences and third order sequences. So in the early Miocene, we have red algae in the lower part, and then bioplastics, including bivalves, gastropods, echinoids, from mudstone to grainstone, but always the bioplastic dominant, not red algae. And then oolitic grainstones, and then microbial facies. But when we go to the middle Miocene, we have another component coming, which is the greenish color, which is the siliciclastic facies, besides the gypsum evaporites. And still, we have red algae, bioplastic, oolitic, and microbials. So we have siliciclastic influx in the middle Miocene. Late Miocene goes back carbonate again. It's red algae, bioplastic, oolitic, evaporites, palaetal, and microbial facies. And as we go from south to north, we'll find like the shallow facies are more dominant here in the south than being in the north. Here we have the blue and golden colors, which is red algae and bioplastics, are much more dominated towards the north, or basically the center of the basin. Here examples and photographs, field photographs for the peritidal facies. This is the swallowtail selenitic gypsum. This is the stromatolites, shale, and sandstone. These peritidal facies. The ramp crest facies, this is oolitic, and here we have the oolitic linoforms. And here I have another example of the oolitic that goes, changes upward into microbial oolitics. You can see the fenestral pores. And here the thin sections for the oolitic, and this is another grapestone that they combined, or they call it composite oils. This is grapestone. The subtidal facies examples, this is the red algae, but this type of red algae that we have it here, they call it oncolytic. It's not symmetrical, it's like flattened. They call it oncolytic, and this type of red algae, usually as the studies in Spain, it deposits deeper, below the weight base. And here the bioplastic facies, and these fossils are echinoids, and this thin sections for the red algae, this is thin section for bioplastics, but not for this outcrop. This is for bioplastics, which is here little backstone facies. This is the representative section. This is the F1 section. And this F1 section, we have 2 second-order supersequences. The lower one, we have just the high stand. We call it SS1. It has just the high stand preserved. The upper one, it's full, or the younger one, it's full second-order supersequence. It has transgressive system tract. It has high stand system tract. So the high stand of the lower sequence represent for the early Miocene. The transgressive system tract for the younger second-order supersequence represented the middle Miocene, and this upper part late Miocene. And these 2 supersequences, we have 6 third-order sequences: S1, S2, S3, S4, S5, and S6. And within these third-order 6 third-order sequences, we have 20 parasequences from PS1 up to PS20. The thing that we note here in the lower part, we have interbidding between bioclastics and red algae. Until we reach this part here, we have interbidding between bioplastics and ooids, which is round crustaceans, getting shallower upward, and then paletal and oolitic, and then come back bioplastics. And here in the middle of Miocene, we start having evaporites, microbial facies, and then evaporite, siliciclastic, the shale, the sand and shale, green sand and dark, the black shale. And then again, this is the middle Miocene where we have the interfingering of the siliciclastic influx, in other words. And then it comes back carbonates, oolitic, microbial, and evaporites. And again, oolitic, microbial with polytons. These here in the, whenever they find the oolitic, they just put the boundary between the Benghazi Formation and Wadi Qatar Formation. And they call, that's where they get the confusion when they say this is like early Miocene and this is whatever above the oolitic will be late Miocene. Because in the types section, when they measured first time, yes, it was true. But when you go far away laterally from that type section, no, it doesn't hold. And the facies and the formations boundaries are not synchronous, they are dichronous. And this is the sequence boundary between which is between the early Miocene and the late Miocene, and the sequence boundary between the 2 second-order supersequences. This is example from the field to show the parasequences. So this is parasequence 4, starting from this small layer, which is the red color here, evaporite, and then all the way shallowing upward, paletal facies, and then another layer, small wacky stone to mudstone layer, almost 20 centimeters. So this is one parasequence, 4, and then another parasequence, flooding, and then shallowing upward, oolitic facies, up to here. And then we start having the parasequence 6, start with the bioturbated wacky stone to mudstone, which is wacky stone mostly, except the upper part, and then start having the the bioplastic facies, which is mostly oysters, all the way up. But this here, it goes up to here. It's not the full section. So this is field example for the parasequences in the field. This is my sequence stratigraphic framework, the southern part and northern part here. What we note here, this is the sequence boundary, the dashed red line. here the maximum flooding surface, the dashed green line. So below the dashed red line sequence boundary is the early Miocene, which is the shallowing upward or high stand system tract of the second order. And above this sequence boundary up to the maximum flooding surface is the deepening upward transgressive system tract for the younger second order supersequence, and then above it, the late this is the whole middle Miocene, and this is the late Miocene starts from here. But in this area, just if you follow this white line, this is just the upper part of the late Miocene. We call it Mycenium, and below it just the Tortonia. So Tortonia is thicker than Mycenium. Here, what we have carbonates in below the sequence boundary, and we have just a little bit of oolitic and microbials in this part. But this part is dominated by bioplastics and red algae. And then as we go up, the bioplastics and red algae started shrinking, and we start getting siliciclastic influx, the black and green in the middle Miocene, start having evaporites, gypsum, besides the carbonates and the microbials. But as we go above the maximum flooding surface, we come back again, carbonate system, which is bioplastics, oolitic dominantly, and microbials, with a little bit of red algae, mostly reworked red algae in this part. So the siliciclastic just comes in the middle Miocene, which is very important. The other thing, these curves, the black curves, are the gamma ray, and as we can see here, we have gamma ray increase, high gamma ray. This is where we put our maximum flooding zone, which is between here and here. But this is the maximum flooding surface, because with the outcrops, it's zone. It's not like a surface you can point at. And after this correlation, we added the stable isotopes, the red lines. This is carbon stable isotopes. And we find out in the middle Miocene, we have the stable isotope, the carbon enrichment. And that's, by using the stable isotope, we had better age control on our work. Here, I forgot to mention this one. This is another sequence boundary between the Miocene and the Eocene, the solid red line. So this is the field photos for the sequence boundary between Eocene and the Miocene, which is the solid line, red solid line. And here the sequence boundary between the early Miocene and the middle Miocene, which is between the old second order supersequence and the young second order supersequence. And this one we have here oolitic grainstones, here's sequence boundary, and here we have this is a close view, we have the biturbation, and then above it the oyster beds. This is the timeline between the late Miocene and the middle Miocene, and in this zone, which is mostly shale and sand siliciclastics, it has carbonate streak here, the whitish color. This is the maximum flooding zone in the study area. After finishing this correlation, we went back to our geographic maps and we mapped and plotted our facies on the maps. And we put them in time sequence. We started plotting the early Miocene, like phase 1 and phase 2. In the early Miocene, we find out we have the blue color bioplastics was dominant, red algae. We have this color is porosities. But the oolitic facies were just on the edges, the northern edge and the southern edge, and they are controlled with or incubated within these two faults. So it was like elongated basin. And then this was Aquitania. This is Portugalian, the younger. The oolitic start growing, and the microbial start growing from both sides, north and south, to the basin, and the blue, the bioplastics, and the red algae shrinking down the basin. So as we go to the middle Miocene and the late Miocene, we start seeing the increase of the progradation of the oolitic and microbial fishes from both sides, and this is the remnants of the deep the subtidal fascias become restricted more and more in the middle of the basin. Until we reach the late Miocene, they become like very little area here and becomes dominated by microbial oolitic, and we have the red color here, evaporites. Starts from the middle Miocene, and we have some evaporites in the late Miocene too. So this is the paleogeographic maps for the study area, and it shows that this basin was controlled by these two faults, and the filling was from both sides, from the south and from the north at the same time. The conclusions for the Miocene sedimentology and sequence stratigraphy: the Rajma group deposited on a ramped system, and it has two super sequences. The first one we call SS1, the second one SS2. The SS1 just has high stand, and it represents the early Miocene. The SS2, it's a full sequence. The transcript system tracks represents the middle Miocene, and the high stand system tracks represent the late Miocene. And these two sequences, super sequences separated by an unconforming surface. These two super sequences has 6 third-order sequences. We call them S1 to S6, including shallowing upward bar sequences. And the early Miocene is dominated by red algae and bioplastics. The middle and late Miocene dominated by oolitic and microbial fascias, besides the association of evaporites. And this study is an excellent analog for subsurface reservoirs because of the good or excellent 3D exposure along 130 kilometers. And the outcrop extends more than that, but this is the limits of my study area. Now the second part, chemostratigraphy. The chemostratigraphy, we chose 4 sections, E1, P1, A1, and H1, H2, to collect our samples. And we measured these four sections, and again, the interval between the samples was 0.5 meters. And we find out the oxygen range was from minus 9.2 to 3.7. The carbon range was between minus 6.7 to 3 per mil VPDB. And what we noted, the early Miocene was richer in both oxygen and carbon. The middle Miocene richer in carbon but depleted in oxygen. The late Miocene is depleted in both oxygen and carbon. So the objectives was to establish the stable isotope curves for the Cyrenaica, to compare them with the stable isotope curve of Cyrenaica, to compare them regionally and globally with the Mediterranean and other oceans and the global, and then that will give us like a better age control over our sequence stratigraphic framework. So the methods, again, we collected 5 O3 samples over 0.5 meter intervals, and we drilled them, sent them to the Texas A&M facility where they have the isotope ratio mass spectrometry, and they did the RMS and HEAL. And then the stable isotope curve is oxygen and carbon plotted, and we put them, we tied them with the sequence stratigraphic frame along the base of the maximum flooding zone in the middle Miocene, which has the high gamma ray and high carbon positive excursion. This is the cross plot. This is the oxygen curve, the oxygen axis and the carbon axis. And here my data plotted based on age. And we put the global range in this black square, the Indian Ocean in this red square, and the range for the Mediterranean in this square. What we find out, we have lots of depletion in oxygen and carbon in my data, which is diagenesis, especially with the late Miocene, with this circle and estric. You can see them here. But in the upper part, you find lots of the Bordighanian and Aquitanian, which is early Miocene. They are mostly enriched in both oxygen and carbon. The middle Miocenes are still enriched in carbon, but depleted in oxygen. Carbon is positive. This is H cross plot. So we plot them again on facies to see if you have facies control or not. So what we find out here, this is the bioclastics. You work with the bioclast red algae and the work, which is basically the subtidal facies. They have the highest positive values here. But the oolitic, the plus sign, you find it all over the place. The rest is peritidal facies, usually in the lower part here. So if we just exclude this depleted lower part and just we look above the x-axis, we still see like, okay, the subtidal facies mostly here, and the round the crest facies, the positive, is mostly on the left side. So still, even the preserved facies still showing facies control. This is the chemostratigraphic correlation. So this is H1, H2, A1, P1, E1. These field measured sections with the sequence, third order sequences. And here the black curves are the gamma rays. And then we added the carbon and oxygen, red and blue for each section. And then we made the correlation. Could you see this in the middle Miocene where we have high gamma ray? We have also enrichment in the carbon. Enrichment in the carbon, which is a very interesting event. We call it Monterey. I'll show it later in the next slide. So with using these, like the field sections, gamma ray, and then tying them with the with the oxygen and carbon, basically the carbon, we had a better H control over our sequence stratigraphic framework. We refined it. Here's the comparison between this is our carbon, the Cyreniacan carbon, and the Cyreniacan oxygen. And this is Zachos carbon, the global, and Zachos oxygen. The first thing we noticed here, we have like a wide range of fluctuations or in our curves, and this is because of the diagenesis. But still, we can see some events. For example, this for oxygen, C1 and C2. C1, we have enrichment here. This is in the oxygen because of the evaporite events.
So I'm sorry, which curves are those?
This is my oxygen.
Yeah, but you have the 4 different sites.
Oh, yeah. This is for A1.
Okay, so why are you choosing that as the one that you're...
This is the one that has minimum diagenesis. Yeah. The others, they're showing like, could you see these tracking each other? Carbon, oxygen. So this is the best representative that has minimum diagenesis.
Thank you.
So, though it has diagenesis, but still we can see some events. I mean, we see evaporites in the outcrops, and still the oxygen telling us, yes, there's enrichment. And this second event here, we have depletion all the way up, which is the late Cerebellian. And this event is Mediterranean event. And this time, we have this connection from between the Mediterranean and Indo-Pacific, this time here, late Cerebellian. And that because due to the uplifting of the collided Turkish and the Arabia. The Turkish and Arabia, they collide here in the early, like early, end of early, and then uplifted end of Cerebellian. So the uplift, it shows depletion in the Mediterranean region. The other events here we find like the B1 and B2 with respect to the carbon. The B1 is the enrichment of the carbon stable isotope, or what they call it, the Monterey event. This is a global event. The B2 is depletion in the carbon, and this is Mediterranean event. And this event is the emergence of the platforms in the Mediterranean region. The other thing we find out, this is the calcium or the carbonate curve. We have 3 intervals of depletion in the carbon, A1, A2, A3. And this is the porosity curve. And we see we have porosity change or increase more or less synchronized with the same interval. And here we have another depletion interval, and this porosity increase to the right. And here we have another interval. In the lower part, we don't have that much change, but in the upper part, we can see there's a lot of depletion. And these events, they call them, they are global events, and they call them low velocity zones. And these are the calcium carbonate dissolution events. And in this sequence here, you can see that in the 3rd order top of transgressive system track. Here, it goes with the 3rd order transgressive system track. And here, it's part of it in the high stand, and part of it is the transgressive 3rd order. But both of these events are within the transgressive system track of the 2nd order sequence. And they say these depletions, the reasons behind these depletions, usually the increase of the ocean's acidity or corrosive, and the enrichment or increase of productivity, that increases the carbon and causing these depletions. So, and the other thing here in the Cyreniaca, we have the coralline red algae. Sorry, not the coralline red algae is like continuous here, but starts increasing upward along the sequence boundary. The other thing in the Cyreniaca, the porieties, which is another coralline just in this area around the sequence boundary. This is how we did the correlation of our curve, the carbon curve. This is the carbon curve of Cyrenaica. This is the carbon curve of the Indian Ocean, and this is the Zachos global. Here the Italian curves, 1, 2, 3, 4, and here's Malta. And this colored zone is the Monterey event. So when it started with the closed area, which is Malta here, and I correlated this part, which is similar to this part here, the Monterey event. And then the depletion part, which is not complete here, so I went from here to this part in Italy, and it's the same exactly. They have the same boundary in the middle Miocene and late Miocene, where you have the platforms emergence and depletion in the carbon. So this is my second boundary, and that's how we get the age control through the correlation of our carbon curves with our neighbor Maltese and Italian curves. So the conclusion in the chemostratigraphic part, the middle Miocene sequence 3, we call it sequence 3 here, this sequence, is the middle Miocene sequence 3, which has most of the events. It has, in the Langen Cerevelian, has enrichment in both in oxygen, which is the evobrite, enrichment in the carbon, which is the Monterey event, and it has the maximum flooding zone. It has the high gamma ray zone, and it has siliciclastic influx. So all of these events happen in the middle Miocene. The C13 enrichment, could be increase in productivity, but we don't have the deeper facies to see the productivity. But we can say that there's a runoff because we have siliciclastic influx in the facies. as I said here, the oxygen enrichment because of the local evaporites. Again, the depletion in the oxygen in the middle Miocene, which is the cerebellium late part, was due to tectonic event, which is the Mediterranean disconnection from the Pacific. And the Tortonian depletion in the carbon oxygen is due to the emergence of the platforms in the Mediterranean area. The calcium or the carbonate depletion events, the first one was in the early Miocene, coincides with flooding surface. The second one, the middle Miocene, which is the transgressive surface of the third order S3. The middle to late coincides with the maximum flooding zone of the second order sequence. There is another thing here. We have negative correlation between the calcium carbonate curve and the oxygen curve. In the middle Miocene, John et al., he interpreted that as a reflection of the siliciclastic influx in the middle Miocene. But I have it all the way, early, middle, late. And the Cyreniacan outcrops, the other finding, preserve complete record of the Miocene. Diagenesis part, in the Diagenesis, we did 4 sections and 4 measured feet sections, and we had 5 O3 samples, and the same thing again, 0.5 meters interval. What we did, we defined facies, textures, grains, cements, porosity types, and diagenesis, like dolomization, dedolomization, replacement, and we added the XRF, silica, magnesium, and manganese. The objective, to construct, or before construction, to define the diagenetic events and process in the Miocene section, and then establish the paragenetic sequence of the Cyreniacan area. So the methods, again, we had 503 samples. We put a blue dye to identify porosity, alizarin iridescent to distinguish between calcite and dolomite, potassium ferrocyanide to stain to distinguish between ferron and non-ferron carbonates. What we did, we used a tripart approach, quantitative, qualitative, and diagenetic. The quantitative just type and percentage of grains, matrix, cement, and pores. The quantitative, which is basically rock textures, grains, and sedimentary structures. The diagenetic part, which is the diagenetic events and process, micronization, dissolution, leaching, cementation, all these processes. So what we come up with? We come up with this paragenetic sequence. We identified our events, and then we put these events in time order. This is the time, direction. By doing that, we get the paragenetic sequences. So the diagenetic process, like micronization, and then cementation, like symmetrical rim, asymmetrical rim, pore filling, dissolution, recrystallization, and we find out them up to 18 events. And we group them into 17s, like seven groups, like early to late. And the other thing, these 7 groups can be put in 2 categories. Just porosity creation, the blue colors, which is dissolution and fracturing, and porosity destruction, the other colors. So we have 1, 2, 3, these porosity creation events, and 1, 2, 3, 4 porosity destruction events. These are the thin sections. This is the example for the symmetrical rim fibers. Here, dogtooth symmetrical rim of cement. And here, pore-filled cement. This is intergrains, and this is intragrains. This is the oomoldic and biomoldic porosity dissolution. We have Jupiter fill. This is the leftover after the dissolution. And here we have the fractures. This first phase filled by carbonates, and then second phase filled cross-cut against the fill of the second phase, and then the first phase, and then filled with silica. And we have cements. Here we have thick crust cements, and we have toroidal fan-shaped cements. Here we have replacement. This is gypsum crystal replaced by silica, and here carbonates, ooids, the cement replaced by silica, the fractured fractures filled by silica and the pores filled with fan-shaped silica. Here the solution seams, they're not styled like this, the solution seams. And here we have the dolomites and the D-dolomite. The D-dolomite is the red color, taking the stain. And now the XRF elements, which is the silica, magnesium, manganese, besides the porosity and the dolomite. This is the microscopic work. The dolomites goes up to here, the maximum flooding zone. If we go to the magnesium, we can see that magnesium goes hand in hand. This is the XRF machine, and this is our preservation in the thin sections. But above this, here we have the manganese. It's just showing up in the upper part where we have the freshwater diagenesis. The silica, it's just spiky. It's almost continuous, except in this part, but always giving me spikes around the time lines between like Aquitanian Bordigayan, I see spike. Mangian cerebellum, I see another spike. Turtonian cerebellum, it has, this that starts spiking but keeps going on, and I have another spike above the Messenian, the Turtonian Messenian boundary, the timeline. And the other thing here we notice that the porosity in the middle Miocene is the highest, average in the early Miocene, and lowest in the late Miocene. Again, this is recap for the phylogenetic sequence, and these all 18 events can be grouped into two categories: porosity creation events, which is the blue colors, the dissolution and fracturing, and the porosity destruction events, which is cementation, fractures, filling. All the others are destruction events.
Can you go back one more? I didn't remember the dolomite types. You have 3 types. What are they?
Yes, the dolomite.
I forgot. You didn't catch.
Yeah, here you have type 3.
What is that?
Yeah.
What is the difference between these different types?
Yeah, the type 3, this is the type of the dolomite that is pure crystal, has no core in it, but type 2, larger crystals, and this is usually cementation type, like coming as cement. Type 2 and type 1, this is a replacement, and type 2 looks like type 1, but the difference, type 2 has a core, dark core. It's not pure.
You showed before the thin sections the difference between the 3?
No, we have the sections. We keep them as extra, just for saving time. But we have them. I can show them.
Okay.
Yeah, and type 1 is just small crystals, small mosaic. I have them in thin sections, but I didn't show them in this. So this is the recap, and here the conclusion for the Diagenesis. So we find out there are like 2 distinctive textures and lithologies around the boundary here, the boundary between the Langian and the Cerebelia, where we have the changes here. So the lower part is dolomitized by plastic rich and red algae rich species, and the upper one is recrystallized through lithic grainstone and microbial species, and both of them, they have silica. And the other thing we find out is 18 diagenetic events in the shallowing of the sequence, or shallowing setting, and this setting never been built. This the Cyreniacan Miocene never been built. And the other thing is the porosity is the highest in the middle Miocene, the lowest in the late Miocene, average in the early Miocene. For the curves, the silica, it's spiky and always like increasing above the timelines between the ages, but it doesn't show like any strong relation with the sequences. The magnesium is in the lower part where we have dolomitization, and the manganese in the upper part where we have the freshwater diagenesis. To recap the whole thing, for the Miocene work, we have 2 second-order supersequences. It contains like 6 third-order sequences and 20 parasequences. The chemostratigraphy, I mean the stabilized, but like the carbon specifically can be correlated regionally and globally. And the age of the Miocene is more wider than before. And even we have like Diagenesis and resetting, but still we can't correlate and see, the events in the Miocene. And the diagenetic events are mainly shallow marine events, shallow marine, and meteoric events, seen like cementation dissolution. And this Miocene carbonates that have been deeply buried. Thank you very much. Would you like to see the slides for the?
No.
No. Okay.
Questions? No, I'm gonna go 2 minutes. I have a quick questions. Which type of material do you use for the stable isotopes? You use whole rock?
Whole rock, yeah, bulk rock.
Bulk rock.
Yes.
Okay. And how do you use the isotope signal for correlations?
Yes. This section here.
Yeah.
This one?
But, yeah. No, this is carbon.
Yes.
Yeah. No, I'm talking about the oxygen.
The oxygen, no, we use carbon. The oxygen
Yeah,
just.
but I think you have one with oxygen.
One with
Correlations.
oxygen here just to show events. This event here.
Yeah, the signal of the oxygen in the whole rock is very sensible to diagenesis.
Yes, I talked to Dr. Grossman about this, and he told me as long as there's something in the rocks telling you that it's like coincide, or I mean not coincide, like it supports. Like if your signal supporting what you see in the rock, you can talk about it. But if it's not, keep away from it. So yes, so
if it gives you the answer you want,
yeah.
then
Yeah. So this is I have like enrichment in the oxygen, and this interval I have evaporates. So